Thank you, Paolo, for the introduction, and let me thank all the organizers for inviting me to this very interesting conference. And let me apologize also because I will not talk about evolution, but I hope what I'm going to say could be interesting in any case. And I will start with a very well-known isoperimetric inequality, which tells you that if you take a set of finite perimeter omega of given volume M contained in a half space, and you want to find the one which minimizes the relative perimeter of omega in the half space, well, this minimizer, as it is well known, is the half ball with the same mass. Okay, this is a very well-known fact, and it is striking then not so many years ago, it was greatly, this isoperimetric inequality was greatly generalized by Choi, Gomi, and Ritoré, who consider the case in which you have the relative perimeter outside a closed convex set with not empty interior. And it tells you that among all possible situations, the best one is the one in which you are in half space. More precisely, given any set of finite perimeter contained outside a closed convex set with not empty interior C, then the relative perimeter of omega in the complement of C is always greater than or equal than the surface measure of the half ball having the same volume of omega. And moreover, and this is the key topic of my talk, if you have a quality, in their case, they prove that if your convex set is smooth, omega is bounded, and you have a quality in this inequality, then necessarily omega is a half ball sitting on a facet of C. So in particular, if your convex set is strictly convex, you will never can sit a half ball on the convex set, and this inequality is always strict. Let me rewrite this inequality by introducing a guy which is relevant for the rest of the talk, that is the isoperimetric profile. This is the inequality. And the isoperimetric profile of the convex set C is the following function. You fix the mass and you take the infimum or the minimizer, well, I will not insist on this point, of the perimeters of all sets having mass M, which are contained in the complement of C. So you take the infimum of all these relative perimeter. And if you consider the same guy for the half space, in which instead you take the relative perimeter of E in the half space among all sets of mass M, and this is precisely given by this quantity, which is the surface of the half ball, then this isoperimetric inequality can be rewritten in the following way. Regardless the shape of the convex set C, the isoperimetric profile of C is always the function which is pointwise greater than or equal than the isoperimetric profile of the half space. Okay, this is what was known, and what is our result? Our means by Massimiliano Morini and myself. Well, we are interested in the case, you see, in the Choi-Gomi-Ritoré theorem, the equality cases were only characterized for smooth convex set, and you will see there is a deep reason for this restriction, while we were interested to the case in which you consider any convex set, not necessarily smooth. And what we prove is that if C is any closed convex set with non-empty interior, and omega in the complement of C is a set of finite perimeter realizing the equality in the isoperimetric inequality, then necessarily omega is a half ball supported on a facet of C. Let me say very briefly why we were interested, well, apart from the intrinsic mathematical interest, but there was a special reason why we were interested in this non-smooth case. It's the motivation comes from the study of vapor, liquid, solid grown on nanowires. And nanowires, in a nanowires, your convex set is a semi-infinite cylinder, usually with sharp edges and non-smooth cross-section. And what you want to do, you want to grow on the top of this cylinder a nanowire, spraying some vapor on it. And in the models used to study this nanowire growth, the energy is the capillarity energy function. That is, if omega is the configuration assumed by the set you deposit on the top of the nanowire, then the energy involved is given by the perimeter, the relative perimeter of omega outside the cylinder, minus a constant lambda, which depends on the material, which is an adhesive constant, times the measure of the intersection between the boundary of omega and the boundary of the cylinder. In particular, if lambda is equal to 0, this energy corresponds to the relative perimeter. And this was one of the cases studied in a recent paper by Irene Fonseca, Giovanni Leoni, and Massimiliano Morini, and myself, where we studied the qualitative properties of local minimizers of this energy. So in particular, to analyze the relevant case lambda is equal to 0, we needed to use at a certain point the characterization of the equality in the inequality, in the isoperimetric inequality by Choi, Gomi, and Ritoré. Before going on, let me introduce some very basic notation. If theta is an angle between 0 and pi, let me denote by S theta, a spherical cap line on a hyperplane, well, the unit spherical cap line on a hyperplane, forming an angle theta with the hyperplane. And let me go back to another well-known isoperimetric inequality, which it's related to the capillarity functional. Now, you have not only the relative perimeter of omega in the half space, but you have only this extra term minus lambda times the measure of the intersection of the two boundaries. And again, a very classical result tells you that given a volume M, among all sets of finite perimeter which have the volume M and contained in the half space, the minimizer of this energy is the spherical cap, which is homothetic to the one that I just introduced, S theta with volume M, sitting on the hyperplane. And the fact that this spherical cap forms with this normal to the hyperplane, the angle theta is known as Young's law of capillarity. It's a general fact, is a general property of smooth minimizers of this energy inside any container, not only inside a half space. Okay. Regarding this isoperimetric inequality, it is interesting to know that we know nothing about the case in which you are outside a general convex set. It would be nice to prove or to disprove. At this moment, we have some reason to believe that this isoperimetric inequality could be true, but also the reason that indicates that possibly for some values of lambda, this isoperimetric inequality is not true. But it will be, in any case, very nice to know if a similar inequality like the one of Choi-Gomi-Ritore also holds when you consider this capillarity energy outside the convex set. In other words, if it is true that given a convex set with not empty interior C and the set omega contained in the complement, that this energy is always bigger than the energy of the spherical cap with the same mass, which lies on a half space on a hyperplane. And even more, it would be nice to say something in the case of equality. So the present, I can tell you that the presence of this coefficient makes the problem very much more complicated than the case in which lambda is equal to 0 and you consider only the relative perimeter. Okay, so now let's go back to the case lambda equal to 0. Because I would like to give you some ideas of the techniques and of the arguments used not only in the proof of Choi and Gomi-Ritore, but in particular in the proof of the characterization of the equality case by Morini and myself. And to this aim, I have to give some more basic notation and to introduce an important object, an important number, actually, which is the total curvature of a set. So now you have your convex set C. You take an open set contained in the complement of C, and you consider the boundary of omega outside C, more precisely the closure of the boundary of omega outside C. Then at every point of this boundary, exterior boundary, you define the normal cone as the set of, let me say, exterior normals, such that this inequality is true. That is, as the set of normals which bound the sigma on one side, that let sigma remain on one side of the hyperplane passing through X and orthogonal to nu. And in particular, let me denote by sigma plus the set of points where there exist in this normal cone a particular normal that is a particular hyperplane pi sub X, such that the intersection of this supporting hyperplane passing through X and orthogonal to nu with sigma reduces only to the point X. So this is precisely the set of points for which a support hyperplane, or even more support hyperplane, exists, but such that they only touch sigma at the point X. Well, once you introduce this quantity, then the normal curvature is precisely given by the measure of the union of all the normals contained in these normal cones at this point. So if you want the image through the Gauss map of all normals corresponding to points where you have support hyperplane which only touch the boundary sigma at one point. Well, the main tool, the main tool of the proof of the isoperimetric inequality by Choi-Gomi-Ritore is this inequality involving this quantity, this total curvature. In this theorem, they assume the convex set to be smooth. They assume the boundary sigma of omega to be a C2 hypersurface with boundary, and also assume that the boundary of sigma intersect the boundary of the cylinder. So the contact line, if you are in 3D, is such that this intersection is orthogonal. Under this assumption, they are able to prove that the total curvature corresponding to sigma, that I go back to the previous slide, is the measure of the image of all normals to such a point, all normals corresponding to support hyperplanes, which only touch sigma at x. So if C is smooth, as in this case, if sigma intersect the boundary of C orthogonally, then this number is always bigger than half the measure of the surface of the unit sphere. Moreover, if equality holds, the boundary of sigma on the boundary of C lies on a support hyperplane to C. So in other words, the image of the normal to this point, sigma plus through the Gauss mech, is always bigger than the half sphere. And if the equality holds, it means that sigma touches the boundary of the convex set on a support hyperplane. But let me stress the fact, which is not a trivial one, that all this is proved under the assumption that the convex set is sufficiently smooth, actually C2 is enough, that sigma is a C2 hypersurface with boundary. And this regularity is crucial because if you consider the minimum problem, the volume constraint minimum problem corresponding to the mass M, you need to show that minimizers satisfy the orthogonality condition, which is assumed in this theorem, which is a necessary condition for this theorem, well, which is included in the hypothesis for this theorem to hold. In our analysis, we had to extend this theorem to a much more general situation. Well, by the way, this orthogonality condition, now, if you think at the capillarity energy, corresponds to the case where lambda is equal to 0 and where the contact angle according Young's law is pi over 2. Well, as I said, we had to generalize this theorem in order to include the case in which you have no information about the regularity of omega, and for the situation in which you have any possible contact angle. Actually, as you can see here, we have a weaker condition than Young's condition. More precisely, we prove the following. Assume C is a closed convex set of class C1, but later on the right assumption will be abandoned, and take any bounded open set containing the complement of C. And let sigma be the closure of the part of the boundary of omega which is outside C. Fix an angle and assume that at any point of the intersection of sigma with the boundary of C, if you take any normal in the normal cone of sigma and you scalar multiply with the exterior normal to the convex set at C, then this inequality holds. That is, it don't necessarily satisfies an angle condition, but you are saying the angles between the two normal, the angle formed between the two normal, between nu sub C and any normal in the normal cone of sigma must be greater than or equal than theta. Then, if this is true, the total curvature of sigma is always greater than or equal than the measure of the spherical cap forming an angle theta with the hyperplane. Moreover, if the intersection of sigma with the convex set is bounded, say you are within a ball of given radius r, for any epsilon, there exists a delta which only depends on epsilon, theta, and r, but of course not on the convex set and not on sigma, such that if you almost realize the equality in this inequality, and if you almost realize the equality in the second one, so your total curvature is equal to the measure of the spherical cap as theta up to delta, then this intersection is not empty, and moreover, the intersection of sigma with the boundary of the convex set lies between, is not exactly contained in a support hyperplane, but lies in a region which is contained between two parallel hyperplanes which are at a distance epsilon one from the other, and which are parallel to a support hyperplane to the convex set. In particular, if you have the inequality in one and equality in two, the conclusion is that this intersection lies on a support hyperplane to the convex set. So let me show by a picture a case of equality in this, which is also a particular type of isoperimetric inequality. Here you have two sets, omega 1 and omega 2, with their boundaries sigma 1 and sigma 2. You can check that at the intersection of these two boundaries with the boundary of the ceiling of the convex set C, this inequality is satisfied. And you can also check that if you take all the possible normals to sigma 1 and sigma 2, they span precisely a spherical cap of angle 3 pi over 4. So you have equality here. And as stated by the theorem, the conclusion is that the intersection of sigma 1 with the convex set C and sigma 2 with the convex set C lie on a support plane to C. Well, in the first case, this is not so interesting because this intersection is just a point. In the second case, this intersection is a line which actually lies on the on C. Let me mention, so in other words, we had to not only to extend the previous isoperimetric inequality concerning the total variation to any possible angle, but we needed to deal with our case to get also a quantitative version of this inequality. Let me mention also an immediate consequence of this inequality is another, in my opinion, also interesting, and as far as I know, new isoperimetric type inequality, which involves a quantity which is a sort of generalization of Wilmore energy. Now, C is any closed convex set with no empty interior, with no regularity on C. We have no regularity on C. Take a bounded open set in the complement of C with minimum regularity in order to talk of mean curvature. So assume that the boundary of omega outside C is of class C11, but no regularity on the contact line between sigma and the boundary of the convex set. If at the intersection with the boundary of C, the angle formed by any normal to x at x to sigma and any normal and prime at the convex set C. Now, I say it again, we have no regularity on C. Then the integral over sigma, over the part of sigma outside C, of the absolute value of the mean curvature raised to the power n minus 1 is greater than or equal than this quantity, which is precisely the same integral evaluated on the spherical cap of angle theta. Notice that this power n minus 1 here that appears on the with the mean curvature makes this quantity scaling invariant. So this is a scaling invariant quantity which only depends in some sense from the angle, in the sense that it's always bigger than the corresponding quantity for the spherical cap. Moreover, and this is a crucial fact for our proof, if equality holds in this inequality and the mean curvature of sigma is different from 0 almost everywhere, then, well, of course, this is not the case in the picture, but if equality holds, then sigma minus C, so the part which is outside C of the boundary of omega, coincides with an homothetic of sigma theta and an homothetic sitting on a phase set of C. So you have that your set omega is a spherical cap sitting on a phase set of C. Okay, of course, if you are in 3D, this is a trivial remark, but this quantity is precisely, reduces precisely to the Wilmore energy, and this inequality tells you that if you form an angle which is greater than or equal to theta at the intersection of the two boundaries, and you form an angle in the weak sense, because we only consider directions which are in the corresponding normal cones, then this energy will be always bigger than 4 times the surface measure of the spherical cap corresponding to theta. Unfortunately, I have no time for, since Paolo, you told me 30 minutes plus questions. I have no time. I had 3 more slides on the proof, but I have no time to say anything about the proof. But in case someone is interested, I can answer on this point. Okay, and I stop here. Thank you for your attention.
Thank you very much, Nicola. So let's thank Nicola for this very interesting talk, fascinating as usual. And we have then some minutes for questions or comments from the audience. I mean, I have one. So you started from these results from Gomi-Ritore, and on the right side, there is the half of the measure of the surface of a ball. I was wondering if one could, and so basically you deduce both the shape of omega in the case of equality, but also that the C is flat. So I was thinking if it could be that in the case in which C is not flat, we could have a case of isoperimetric inequality, but on the right side, not half of the ball, but like an intersection of the ball, a portion, something depending on C. So like, for example, if, I mean, I understand that if C is very complicated, there is also the problem that it could translate on C. But if something is periodic, for example, so I mean, maybe there is one could have like on the right side, like a portion depending on C, a cut of the ball that depends on C, and then yeah, I don't know if I explained me well.
No, I think I have understood. Okay, if you, well, as I said, if omega is not the boundary of the convex set is no flat part, you cannot expect to have equality here, as stated by the theorem. Yes. Well, you may expect something bigger bounding these relative perimeters. Well, at least if the convex set is bounded and has bounded curvatures, the quantity you can put on the right-hand side is something bigger than this quantity, which is the surface measure of the ball with the same volume, but that will depend on the curvature, on the bounds you have on the curvature. So you may imagine a different inequality that tells you, okay, if you are dealing with the convex set which are within a ball of fixed radius and which have equibounded curvature, then the minimum of all these perimeters at a given mass are bounded by a constant, a universal constant, which only depends on these quantities.
Okay. Yes, actually, I forgot that you needed also C to be convex, so something periodic, if not. But okay, maybe one could also have something depending on C here, in the case in which C is not flat.
Well, as I said, if you want, if you assume C is smooth, you may have a bound which only depends on the diameter of the convex set and on the bounds of the curvature, on the curvatures.
Okay, thank you very much. We have a question from Shrew.
Professor, I have just two questions. So first question is, can you say anything, for example, in the anisotropic perimeter case? And second one is, if I'm not mistaken, in the full RN case for isoperimetric inequality, one needs a Steiner symmetry and some such kind of tricks. And what would be the replacement of Steiner symmetry here in this situation?
Okay, let me first answer the second question. Unfortunately, Steiner inequality here is completely useless. Steiner, you can only use Steiner inequality to prove the isoperimetric, well, to prove this isoperimetric inequality. Well, this is actually even simpler. You just do it by reflection, by a reflection argument. But if you want to, for instance, to prove the isoperimetric inequality involving the capillarity energy and you are not outside any convex set, but you are inside the
hyperplane.
The half space, then actually, if you want to prove this isoperimetric inequality in the case of the half space, then you really prove it, for instance, by using Steiner inequality. But for a general convex set, you have no symmetries at all. So Steiner inequality is, as far as I can see, useless. Concerning the other question, what happens if you have an anisotropic, the anisotropic perimeter? This is a much more complicated question because what you could expect? Well, first of all, as far as I know, even the case in which you are in a half space is not known. So you should first understand what happens. Okay, suppose that you have an anisotropy and your guy is not a ball. You're minimizing guy for the isoperimetric inequality in the Euclidean space with that anisotropy is not a ball, but is a polyhedron. So it's not clear to me what happens to this relative inequality if you are in a half space. So you should first to study this case and then consider, and then probably to see what happens if you are outside any convex set. But as far as I know, there is nothing known in the anisotropic case.
Okay, thank you.
Okay, we have a bit of time for another question from Gianpaolo Leonardi. Please unmute yourself. Okay, thank you.
Yes, okay. Ciao, Nicola. Thanks for your very, very nice talk and result. So my question is about this idea, which probably doesn't work. And I just wanted to ask you why, where the problem. So trying to instead to smoothen the convex set. So maybe in some careful way, and solving the problem for a sequence of smoothed convex sets, and then try to see what happens to the limit. So where's the problem with this? Maybe too naive.
No, Gianpaolo, you got the right idea. The idea is as I said, Choi, Gomi, and Ritore characterize the equality case when the convex set is smooth. So if you want, as you know well, if you want to characterize the equality case in the non-smooth case, you can do this kind of approximation, and is precisely what we do in the proof, but you need to have your ingredients in a quantitative way. So you need not only to have a quantitative, an isoperimetric inequality of the type, you must have in some sense a quantitative version of the isoperimetric inequality. And this is precisely what we do. But so the idea is this, and you are right. So the idea, if you want, is very simple. The implementation is very much complicated, and I explain you why the implementation is complicated. The reason is that as I said, the fundamental ingredient of Choi-Gomi-Ritore proof is the fact that you have this inequality involving total variation as long as you have a smooth convex set, a smooth guy intersecting orthogonally the convex set. In our case, we do the approximation, and in order to pass to the limit, we are bounded to consider the minimizer of the perimeter. Okay, suppose you have the set in which you have equality, the guy for which you have equality. You want to show that this guy is a half ball. Okay, so you do the following. You approximate the convex set with something smoother. Okay, let me show the picture. You simply approximate. So this is the guy for which you had the equality at the beginning, omega naught. So what you do, you approximate your convex set with something smoother, and you consider the isoperimetric profile inside this container. Why you have to be confined inside the container? Because then you have to pass to the limit, and you want your minimizers run away to some other minimizer. But then regularity becomes an issue at the intersection. First of all, in general, you don't have full regularity at the intersection because there will be always on the contact line some singularity. So you don't have in general the validity of the Young's law. But nevertheless, we are able to show that for these approximating minimizers confined in omega naught, you have a weak form of Young's law, precisely the weak form which allows us to use this theorem. But to prove this weak form of, well, you have several problems here, the convergence of all the quantities and so on. But the main problem is to prove this weak form of Young's inequality is the most delicate technical tool, because now you deal with something which is not smooth at all. And which not only this, but it minimizes the perimeter under an obstacle condition.
Sorry to interrupt.
Thanks very much.